Hi, my name is Michael Lin, and I'm here today with Lindy Villapantu and Love Agarwal from IBM. We're here today to discuss decision optimization, and specifically, how organizations can simplify complex business decisions using data science and technology. First off, what is optimization? It's essentially finding the best combination of inputs to maximize or minimize an output. For instance, imagine you're moving from one apartment to another, and you have to move all of your objects with the moving van. So what do you want to do? Well, you want to maximize the space in the moving van. So you start packing in your objects as closely as possible. One by one, you realize you can almost fit all of the objects into the van. But when you get to the end, you realize there are just a couple objects which can't fit, but you still have some space in the van. So you try again, see if you can make it all in one trip. So this time you start from outside to in with the larger objects to really maximize the space. And this time, you get even closer. Once you get to the end, you realize there's only one object that you can't fit in. Unfortunately, you're most likely going to have to take 2 trips. If you do manage to find the perfect optimal outcome, that's fantastic. But it'll probably take a lot of attempts. Even a problem like this can get really complicated. But imagine you're a retailer and you have to ship objects all over the country. You have to find the optimal driving or flying routes. You now have time constraints, weight constraints. It simply gets too complicated to do by hand. So you need to automate this process. And using this data science and technology, you can make this process repeatable and efficient. Now I'm going to pass it over to Lindy Villapantu to talk a little bit about the use cases before Love talks about how you can really operationalize optimization in an enterprise.
Thanks, Michael. So, decision optimization can be utilized for pretty much every industry. In the distribution market specifically, optimization is extremely helpful with problems like production planning, route optimization, inventory optimization, and operations planning. And like Michael was saying, decision optimization technology can tackle highly complex problems and also make it easier for users to factor in constraints, trade-offs, and multiple objectives for faster and better answers to questions like how can we optimize delivery routes for optimal savings, and when should we reduce SKUs or introduce new products? So let's take a look into 3 different use cases within the distribution market. So, within the travel and transportation industry, transporters have a finite number of trucks, warehouses, and drivers, but an infinite number of potential delivery addresses. On any given day, they need to decide how many drivers and trucks to put on the road, but they also need to keep the cost of equipment, fuel, and drivers to a minimum while being able to meet delivery commitments. So, IBM has been working with a leading bulk tanker transportation company to combat these challenges. Using optimization software, IBM helped this company find efficient routes in near real time that found solutions for 1,500 orders, 800 tankers, and 500 drivers with a 5-day horizon in less than 10 minutes, which is a problem space that contains more than 1 billion feasible assignment scenarios. And this model enabled huge cost savings and also supported growth for the company as well. And in the retail industry, decision optimization is used to help streamline production, product assortment planning, warehouse replenishment, and pricing and promotions with decision intelligence. One important use case within retail is inventory optimization. So, stocking the right products in the right quantities at the right location requires precision, and decision optimization software helps firms manage their inventories to meet customer demand while also reducing cost. And it also enables firms to compare multiple planning scenarios using what-if analysis to then be able to choose the best option, all while avoiding under and overstocks. So, for example, the largest manufacturer of greeting cards in the United States needed help to develop an assortment mix for their 42,000 stores. They needed a solution that satisfied specific needs to tailor the display for different demographics and also to define business rules for mix and placement. So decision optimization solved for the best mix to maximize sales given the footage available at the store by assigning the proper mix on expected sales. And then finally, in the airline industry, decision optimization can be used to help with problems like crew and aircraft scheduling, aircraft maintenance routing, and ground operations, just to name a few. And with ground operations alone, airports need to optimize gate assignments, check in counter and luggage allocations, and ground staff scheduling to ensure that they're saving the most money and also reducing costs. IBM has been working with ground operations at multiple airports in a major European city to use our decision optimization solution to deal with these challenges. The results were a 20 to 75% increase in staff production and less than a minute usable roster generation, which saved them overhead costs and also increased their profit as well. And these are just a few of the use cases that we have, but there are many more in the distribution market and also in every industry as well. So now that we have a good idea of why decision optimization is useful, Love is going to conclude by discussing how you can operationalize decision optimization in an enterprise.
Thanks, Lindy, for sharing with us those use cases. I want to now pivot our discussion to how do we actually operationalize decision optimization within an enterprise. So when we talk about successfully leveraging DO, there are two perspectives that we must consider. There is a strategy component and a technology component. On the strategy side, an organization must first start with picking the right use case. So Lindy shared a few examples with us, and they all fall into four main categories. The first is resource assignment, in which we're matching resources such as workforce, equipment, to specific jobs, events, or places. The second is scheduling, in which we want to manage the order of tasks or events to be done in a given order with specific rules, start, and end times. Then we have selection and allocation problems, in which we have to optimally choose a few options from a large list of possibilities based on our constraints. Lastly, we have supply and demand planning problems, where we must quantify things like inventory or raw materials over a period of time to determine the optimal mix that satisfies our demand. Each of these use cases must be explicitly defined upfront and backed up with quantitative metrics and constraints that we're trying to achieve. Next is the idea of trust in outcomes. It is imperative that we develop a culture in our organization that values and trusts the output of our optimization models. It does not benefit the business if end users disregard the suggestions from our models and continue to rely on their instinct. However, we can foster this kind of culture by incorporating feedback from our end users as to what additional information to consider in our models. The second piece is model explainability. This means that our optimization models should not be happening in a black box. Our data scientists should be able to explain why certain outcomes occur based on all of the inputs. Lastly, we must foster decision optimization and data science skills internally and build a practice which allows for users with various technical and industry domain skills to collaborate on optimization projects. So that covers the strategy side at an overview level. Now let's move on to the technology component. So we start with two main concepts that are critical when evaluating any platform: the freedom to choose a technology and the freedom to choose a methodology. On the technology side, an optimization platform should support various modeling languages, including open source Python to leverage wide availability of skills, as well as specialized languages like OPL, which are purpose-built for substantially simpler and shorter code. On the methodology side, an optimization platform should support methods of building models, including fully programmable environments to utilize languages previously mentioned, as well as a guided wizard-like approach to assist less technical users with building the same high-quality models. This can be further enhanced by allowing less technical users to build baseline models through the assistant and handing them off to more technical users for customization in a programmable environment. This way, we are fully leveraging our internal skill sets. Lastly, an optimization platform needs to also consider what we do after model development. How do we deploy and infuse these models? So we should have the ability to deploy models at scale in the same platform and make them available for consumption by business applications through standard REST APIs. In addition, we should also be able to directly see the impact of these optimizations on our operational and financial plans by integrating with financial planning tools like IBM Planning Analytics. These are all the capabilities that enterprises should demand from an enterprise-grade optimization platform. And we have made this platform available as IBM Cloud Pak for Data. I invite you to learn more about what Cloud Pak for Data can do for your business.